So training a recurrent neural network. So we have seen that to train the MLP, we can use the backpropagation algorithm. So can we use the same backpropagation algorithm to train a recurrent neural network or RNN? So let's see how can we use it, right? Now let's say this is our RNN, right? So in the now we have in the forward phase, we'll be producing these outputs. We'll be getting these outputs. O1 is equal to f of w1 into xi1. O2 is equal to f of w1 xi2 plus w2 o1. So O3 is equal to f of w1 xi3 plus w2 into O2, right? So similarly, O4, if I write O4 is equal to f of w1 xi4 plus w2 into O3, right? So that is O4. So this is the forward phase in which we are getting the output. And similarly, I can write final output y hat is equal to g of w3, because the activation function here is g, right? G of w3 into O4. So this is the forward phase in which we are getting the output. And finally, we compute the loss. This loss means difference between the predicted output and the actual output. The difference in actual output and predicted output. This can be a simple log loss kind of thing here, right? So finally, we compute the loss. And now, in order to train this network, we must be able to update these weights over time, right? That means I must be able to update this weight, then this weight W1 in this step. This is time t is equal to 1, this is time t equal to 2, time t equal to 3, time t equal to 4. I must be able to update this weight in this particular step. I must be able to update this weight in this particular time step, and I must be able to update finally this weight, same weight, at time t equal to 1. So that is how I can train this network. So I must be able to update these weights over time, right? So let's see how can we compute the how can we update the weights by computing the derivative, right? We must be able to compute the derivatives of loss with respect to weight. So how can I let's see how can we compute the derivative. So derivative of loss with respect to let's say this W3 dou W3 is equal to derivative of loss with respect to yi hat, right? And then derivative of this yi hat with respect to W3, right? So that by using chain rule, I can compute this derivative of loss with this W3. Right. Now I can also compute the derivative of loss with respect to O4, right? So derivative of loss with respect to dou O4 is equal to derivative of loss with respect to yi hat and derivative of yi hat with respect to derivative of O4, right? This one. Now, in order to update this W1, how can I do it? Derivative of loss with respect to derivative of W1 is equal to at time t equal to 1, at time t equal to 4, at time t equal to 4, right? So derivative of loss with respect to this W1 at time t equal to 4 is equal to derivative of loss with respect to yi hat, and then derivative of y hat with respect to O4, derivative of loss, derivative of yi hat with respect to O4, right? This, and then derivative of O4 with respect to W1, derivative of O4 with respect to W1, right? So that's how I can compute the derivative of the loss with respect to W1, and then by using the formula which we discuss in MLP, new weight is equal to old weight plus eta times derivative, right? That by using that formula we can compute the new weight, right? So if we are able to compute the derivatives, we'll be able to update the weights, right? But now similarly we can compute the derivative of W2, right? Now the problem here is at this time step when you come back from here, from here to here, right? So when we will compute W derivative of loss with respect to this W1 at this time step, right? We are going to multiply a lot of these partial derivatives, right? Because partial derivatives in this layer, in this layer, in this layer, in this layer, and if there are, let's say, many layers, let's say 10, 20, these are not layers actually, right? So these are the steps, time steps. These are the time steps, right? The same neural network is being fed with a different input at different time step, right? So these are not layers, but if there are, let's say, 20 time steps, so you'll be multiplying a lot of partial derivatives. And if this units, activation units here are sigmoid or tan h, right? So you will be running in the problem of vanishing gradient, right? So this is one problem here, because when you compute the derivative in this particular step, while coming back from the beginning, and you will be multiplying a lot of partial derivatives all throughout, and that's why this value will be too small. The derivative here will be too small, and if the derivative here is too small, then the weights will not be updated, right? So this can cause a problem of vanishing gradient. So we'll see how to solve this problem by using the other types of networks, right? So, but this is the problem with this training RNN, if we are using this sigmoid or tan H activation units here, right? So, but that is how you can train the this RNN, right? So this is back propagation. In the back propagation, we just follow the arrows in the reverse direction, right? In the reverse direction of this, right? In the forward direction, we go like this. In the backward direction, we go like this, right? Computing the derivatives of weights at that particular time step, right?